We've looked at some of the impacts of climate change, and the oceans are a big site for that. And we've already seen the Chasing Corals documentary. And you've probably, if you're kind of following this in order, you've probably seen the whole kelp forest uh, problem that we looked at with documentaries and the whole story of the basically the urchin barrens forming. So the collapse of an entire coastal ecosystem basically is that part. There's also some other things that happen with global climate change in the ocean. And one of them is something we ran across at the very most basic level when we did climate change itself. And that is one of the pieces of evidence for climate change is that the oceans are rising. And the reason that that's evidence for climate change in the area of warming is because warmer ice or warmer air melts ice. Ice runs off the glaciers into the ocean, and more water in the ocean means higher sea level. And also, warmer oceans. Oceans are receiving about 93% of all the extra heat trapped in it from greenhouse gases. Warmer oceans also thermally expand, making sea level rise as well. So those are basic causes, and we'll hit a little bit of that here again, but just to review that first. So what this document is in Moodle is it's just more about that sea level rise. Okay, the best starting point. It's really some really good science, kind of popular science level, but very much based on the state of the art in science. Is in the Guardian newspaper, based in the United Kingdom. They have kind of a U.S. version of it. It's really top stuff for just kind of learning the basics. So what I want to do here, I just clicked on that very first link here. And so 3 things you don't know. Okay, well, some of you may know some of these, but let's look at them anyway. And I'm going to pull this down a little more here. So melting ice sheets are a major cause of sea level rise, but not in ways you might expect. So some of this is really counterintuitive stuff. And what I like to say as I start this is it's simple to think of, oh, if I'm putting more water in an ocean basin, it'd be like a bathtub. Water would rise everywhere in the bathtub at the same amount. If it rises an inch on one side, it's going to rise an inch on the other. But that would be wrong. What's going on? Okay, so this is what we're going to look at as this sort of counterintuitive stuff. It's really quite fascinating. So let's have a peek. Let's just read the narrative here in the lower left, the box there. Global average sea level is rising, but it doesn't happen at the same rate everywhere. The darker blue colors indicate where the sea level rises the most as Greenland loses ice. The red shows where the sea level goes down. So check it out. Wow. So it's saying that sea level goes down around Greenland when the ice melts? Yeah. Or if you're in the Marshall Islands, where some of our students at Western Oregon University are from, I'm not sure I have any of you in this. I may have 1 or 2 students from there this term in this class. Send me an email, by the way, if you want, if you are, it'd be interesting. But so we have some areas where it's rising a lot more and some areas where it's actually going down. What's going on? So, as I said, the basic causes are ocean warming and melting of ice sheets, but the sea level rise itself is counterintuitive. So, let's follow that narrative a little bit. You might expect that sea levels would rise most where ice melts. However, a range of complicated influences doesn't mean this is the case. And so, the nice little block diagrams here give us a good start. Okay, so this is the block diagram. This is Greenland. Okay, and as you look at this, that's the ice sheet, and then this is the water, and then this is somewhere far away in the tropics. To kind of think about that a little bit. So ice sheets attract water, so you can see that water is actually being pulled up. Obviously, the relief or the scale of this is exaggerated, so you can see it, but there is a little bit of gravitational attraction, and so this because the ice sheet itself is massive, has lots of weight. It actually attracts a little bit the water towards it. Okay, now when you melt the ice, now there's less gravitational attraction. So from here to here, it melted, and there's less gravitational attraction. So that water that had piled up near the shorelines now has moved away, and the melting ice, a lot of it now is observed on the other side of the Earth, very far away. Okay, there's less gravity now pulling the water to Greenland, and so it flows away even as there's more water in the ocean basin itself. So that is the very first concept. Got that? Okay. So again, losing some of its mass means it has less gravitational attraction. The water flows away. This is true of Greenland and Antarctic ice sheets melting, by the way. So the same thing's happening on the other side of the planet. So ice melt from the last ice age affects today's sea level. Okay. So what happens here as well, then as ice melts, the land underneath it rebounds. Okay. And that's a fairly quick process. The very first part of it is quick. And it happens then. It starts right away, but it takes a while, is what I'm saying. And you can see here the rising land level can make the sea level locally actually be farther away, okay, because it rose up. As you can see, the difference between this and this, the land is higher, so the sea is relative to the land is actually lower, even though the sea itself went up. So those slow adaptations called glacial isostatic adjustment take place over many thousands of years, very, very slow. The ice melts and the water enters the ocean. It also moves our mass around a little bit of the planet, and that makes a little bit of a wobble on its axis. Antarctica and Greenland would be, of course, the two primary places that happens. Okay, so that's just a little bit of a starter on this. Now, let's go to more. There's a lot more, and I just barely got our feet wet, so to speak, with changes in sea level. This one here, I want you to read. There's some pretty interesting stuff on it. And this one as well, just go look from 10 to 14 minutes. It talks a little bit about how scientists are collecting data. So just jot a note or two down on each one of these two narratives, especially this video, I mean, and then just kind of follow this to support everything we've done. So what this does is it's kind of a summary statement of a lot of what is known. And what I'm doing here is to try to explain it to you in a way that's kind of comprehensible. And then once you do that and read this, you'll get it better in hand. Okay, so let's look at a few of the basics of overall sea level rise. One thing to say is that the sea level rise is accelerating. The rate is practically doubled, and it's up to, and actually it's even a little more than this now from what I saw recently. So about 3.2 millimeters a year since 1993. So it's accelerating. The process science to know about overall sea level rise. Okay, the first thing is just to understand a little bit about glaciology. In glaciology, glaciers gain mass through snowfall. Okay, it makes sense. The more snow falls on the glacier, the more mass you have there, and gradually it compacts down and becomes more like glacial ice. And glaciers lose mass through melting and sublimation. Okay, so where you have ice and it basically becomes gas or water vapor, that's called sublimation. It can go either direction. But when you're losing mass, it becomes part of the atmosphere, the water from the ice does. So they can lose mass through both of those, okay? So if a glacier is growing, then it has either more snowfall coming in and or less melting. So if it's growing over time, it could be a combination of the two or one or the other. So now the fact that we're losing mass means that either it's getting warmer or we have less input through snowfall or some combination of the two. Okay, and for the most part, the glaciers are losing mass because of less snowfall, or excuse me, because it's gotten warmer. But in some cases, the snowfall amount changes too. So both of those have to be considered in the equation. There are a few places in the world where glaciers are growing, and those are areas where adjusted weather patterns have led to a lot more snow. And more snow can mean a slight change in mass, but that's actually very much the exception, not the rule. Okay, so the second part is that melting continental ice sheets and alpine glaciers, those of mountains, and thermal expansion each contributed almost 1/2 of sea level rise in 2010, but now non-sea ice melting contributes double the sea level rise as thermal expansion. So basically, it used to be thermal expansion, it gets warmer, it makes more volume, and the actual melting itself with more water there. Now the melting non-sea ice is double the amount of contribution to sea level rise as is thermal expansion. Another less important but still worth noting example, I actually gave that on a test last term. Most students didn't get this. I do remember talking with them about it, but just remember this one too. It's kind of strange, but we are losing water storage on land. Some of that is because we've lost water out of a lot of our aquifers that we're pumping to do a lot of irrigation. Southern Idaho is a place where that's happening. Much of the Ogallala Aquifer in the central part of the United States, that's also happening in the Great Plains. So decline of water storage, that also is contributing to a little bit of a raising of sea level. A lot of that water then runs into the sea that we irrigate with. Melting sea ice does not contribute to sea level rise, which is something that we actually hit on a while back as well. So if you have ice on the sea already and it melts, it doesn't contribute to sea level rise. It's sticking up, but basically as it melts, its density decreases. So sea levels, now this is the stuff we're really focusing on this unit though. Sea levels sea levels change more relative to land in some places than others. Here's one. The U.S. East Coast sea level is rising 2 to 3 times faster than the global average. Why is that? Okay, we'll look at all that in a bit. The second is in Scandinavia, basically Finland, well, not so much Finland, but Norway, Sweden, particularly, maybe the northern parts of Denmark, you could think of that region broadly speaking, is an area where sea level is falling. And that's because of mantle mass flow. We'll get to that in a bit. Here's one. China's Yellow River Delta is rising 9 inches a year. Sea level is rising 9 inches a year. That's a big problem. Shanghai, which is a coastal city, and more or less in the south of China, if we get 3 degrees C of sea level rise, I saw a recent article on this, basically almost the entire city is going to be underwater by the end of the century. Tropical Pacific islands far from Greenland and Antarctica are seeing large rises. Okay, so much of the Pacific islands that are tropical, unfortunately, are getting more sea level rise than much of the rest of the world. Tragic, catastrophic, people have nowhere to go. Continental glaciers, as they melt, have 2 key effects. Okay, their weight has depressed the Earth's mantle below and caused it to bulge out adjoining areas, and melting quickly causes an elastic rise of land under where the ice was. We saw that earlier. Basically, the ice is gone, less mass, it goes up. Okay, but there's a more slow process called mantle mass flow, which will also move toward where the glacier was over thousands of years, slowly raising land there. So there's a region which includes Finland, but also Scandinavia, where some areas are rising at 9 millimeters a year, even many, many years after the massive ice has been gone. Okay, and we're going to look at that in just a moment here. The gravitational attraction of the ice on nearby seas decreases as it melts, so adjoining sea level falls as continental glaciers and ice sheets melt. So as you saw in the Guardian article above, just kind of giving that as a formal statement here, their ice sheet melting of Greenland and Antarctica lowers sea level nearby and increases it far away from each. Okay, so just to spend, actually, you know what, we'll stop this one. I'm going to make a new YouTube video and actually look at this mantle mass flow. It's kind of a complicated subject. I want to do a good job on it. So we'll be back with a new video.